In this video, we're going to look at Lamy's theorem and its relationship to equilibrium of forces. Okay, now if three forces are acting on a particle and they're in equilibrium and the angle of forces, there's no one between them, then these relationships listed here hold, and I'll show why that is in a moment. If these three forces are in equilibrium, that means the net force on the system is zero. And so when we do the vector addition of these forces, we add them all up. The triangle should close and the three vectors should close on each other. And there should be nothing left over. There should be no need for an extra total net force because these will sum to zero. So a vector triangle is formed that's closed. There's no leftover bit that needs an extra vector to fill it. Okay, so to show you why these relationships might hold, let's take, for instance, F2 here. And what we're going to do is just shift it up the page so that the beginning of F2 can be added to F1. So we're going to need a vector here like this. Okay. Not very straight, is it? I'll just get rid of that and try again. All I want to do is shift it up the page, keep it parallel, something like that. Okay, that'll be our F2. Now you see the angle between F1 and F2 is theta 3. So this angle up here, okay, this angle up here is theta 3. So this angle in here is going to be 180 degrees minus theta 3 because this is a straight line along here. Okay, let's now take F3 and we've got to add this in here. I've not done a very good job, my apologies. It's not looking very impressive, but anyway. Okay, imagine that this one here is parallel to this. Okay, we just shifted it over. My apologies, I haven't really done a good job there. Okay, so the angle then between F2 and this is F2 and this is F3, and the angle between F2 and F3 is theta 1. Okay, so that should be, well, I've lost track of my diagram here. That should be F2 and F3. That should be theta 1 there. So in here should be 180 degrees minus theta 1. Okay, and this is of course F1. All right, I'm not going to add any more to that diagram, otherwise it's going to get really messy. Okay, now what that means is if you look at the sine rule in operation now, you can see that F1, now that we've got our closed triangle, F1, this side over the sine of this angle, okay, F1 over the sine of 180 degrees minus theta 1 is equal to F3 over the sine of this angle here, which is 180 degrees minus theta 3. So F3 is sine 180 degrees minus theta. And if we put F2 in here, we would have here F2 is this side here over the sine of this angle, which would be 180 degrees minus theta 2. Okay. By the symmetry properties, sine 180 degrees minus theta 1 is the same as sine theta 1. All right. That's just by the symmetry properties. Okay, so what we can now say is that you can use these relationships here directly from the closed triangle. If you don't have the closed triangle, it doesn't matter because it's the same as F1 over sine theta 1, F3 over sine theta 3, F2 over sine theta 2. Okay, and by the symmetry property, sine 180 degrees minus theta 1 is the same as sine theta 1. Okay, if you just have a diagram like this, okay, there's theta, then this is sine theta, and if you do 180 degrees minus theta, that's this length here, that's the same as this one. So by the symmetry properties, they're the same. So for Lamy's theorem, we can use this sine rule here if you've got three forces that are in equilibrium forming a closed triangle. If they're in equilibrium, the triangle will close. There's no leftover bit where the vectors don't join up and therefore needs an extra vector to make the sum equal. All right, so let's have a look at an example of where this works. Okay, now we can use it in either form. If you close the triangle, you can do this. If the triangle's not closed and it's like the original diagram in black here, then f1 over sine theta 1, f2 over sine theta 2, f3 over sine theta 3. Okay, let's have a look at our example. We've got a block on an inclined plane, 30 degrees. Okay, here's our block. We draw in our center of mass, pretend all the mass is concentrated in that center there, and all the forces act through that center point. All right, so you've got a reaction force coming out perpendicularly out of the plane. Okay, you continue the line down into the plane. Weight force acts down vertically towards the center of the body on which the planet or whatever gravitational body it's on, causing the G. And then on the plane here, you have the block sitting on the plane. You have a force up the plane, pushing up of 49 newtons. And all of this is in equilibrium, holding the plane, holding the block stationary on the plane, or the block can be moving with constant speed on the plane. Okay, but there's no net acceleration. All the forces balance. So the block either is at rest on the plane or in a state of constant motion, constant speed on the plane. Okay, constant velocity, so single direction. The three forces are in equilibrium. All right, so we can write this weight force mg carrying down over the sine of 90 degrees because this is 90 degrees in here. Okay, we have our coordinate system like this, plus, okay, up the plane, if you like, and out of the plane here, positive. Okay, so this is 90 degrees, they're perpendicular to each other. Next one, this 49 degrees. Well, what's the angle here? That's 90 subtract 30, so it's 150. My apologies, 180 subtract 30, which is 150 degrees. So you've now got 49 over sine 150 degrees. And then finally, you've got r over this here, which is 90 plus 30 to give you 120. So r over sine 120. So take your pick which ones you're going to use. mg sine 90 equal to 49 over sine 150. So mg equals 49 sine 90 degrees. Just multiply both sides by 90 degrees. So 49 sine 90 degrees over sine 150 degrees. Put that into the calculator. That gives you mg is 98. Right, and then m is 98 on G, and m is, if you take 9.8 for G, I didn't say that, but if we just did G equals 9.8, instead of saying 9.82 or anything like that, then we'll get exactly 10 kilograms for the mass. Here, r over sine 120 is equal to 49 over sine 150, so let's just multiply both sides by sine 120. We get r equals 49 sine 120 degrees over sine 150. Into your calculator you go, 49 root 3 times n. Okay, and what you get here, r is approximately 84.87 newtons. Okay, assuming all of that's in equilibrium, then Lamy's rule applies, but only in the case of equilibrium, so that the three vectors, and there are only three vectors involved, and they all sum to zero, allowing you to use the sine rule in one form or other. Okay.